Hello, my name is Mustafizur Rahman, and I'll be sharing a short teaching module on quantum computing and quantum information. Um, the fundamental unit of quantum information is called a qubit or a quantum bit of information. So there are various quantum architecture for generating the qubit, and one of them is the superconducting qubit, where the superconducting qubits are often called as a transmon qubit based on the transmon technology, which is based on some sort of Josephson junctions and supercapacitor based artificial atoms of few nanometers dimension. And these kind of artificial atoms are typically considered to generate various energy levels like an atom, and some of the energy levels are considered as the basis to represent the informations, for example, the ground state and the fast excited state. In contrary, in spin quantum system, sometimes the up spin is called the Ket1 and the down spin is called the Ket0 or vice versa. So if we compare with the classical CMOS based technology, where we represent the 0 and 1 as the unit of information or bit of information, typically they are the voltage level, which we generate by controlling the depletion width and the flow of electron within the transistor, right, as shown here. A quantum information, if we follow the quantum postulates from physics, these are the quantum states typically represented by vectors. And we know any vectors, if you want to represent, for example, in a 2D coordinate system, we need two basis system, like an x-axis, y-axis, or the horizontal axis and the vertical axis. So if you typically consider this unit circle, this Ket0 is this point, where Ket0, the component are 1, comma 0, or in a column vector form, this is 1, 0. And similarly, this North Pole Ket1 can be written as 0, 1. This is like the y component is 1 and the x component 0, right? So any vector we can represent as say a times 0 and b times Ket1. These are two typical basis vectors. So similarly, we can, in a n-dimensional space, we can represent with n basis vectors. And any operations we try to perform on the vectors, there should be some matrices. And to follow the quantum postulates, the matrices has to be unitary matrices. In general, these vectors can be represented in this form, like some coefficient times some basis representations, what we call as superpositions. That means it exists in a complex linear combinations of two or multiple states. Here it is two. So I can represent the vector in terms of computational basis, eigenbasis, Fourier basis, or any arbitrary basis. To create superpositions on a quantum circuit, we typically use the Hadamard gate, and the Hadamard gate is a 2 cross 2 matrix, 1, 1, 1 minus 1 are the components. And if you can simply multiply this matrix with the secant 0 factor, you can see that the component, resultant component will be 1 and 1. So which is basically 0 plus 1 or the plus state. And if you repeat the experiment for several times, you can see that how many times you are getting 0 and 1 will be theoretically half and half. For example, in the 1,000 experiments, we see 506 and 494 be the number of counts or the histogram. Entanglement is another important phenomena which we see typically for the composite system, two or multiple system. In a two system quantum entanglement, let us take an example to understand this. So one of the entanglement state is called a Bell state, which is 0, 0 and 1, 1. How to prepare such entanglement? Suppose we initialize with two qubits Q0 and Q1. So if you apply to Hadamard gate, so quantum system can be represented as a composite system, and the mathematical representation is performed with the tensor product form or the matrix canonical product form. So if you apply two Hadamard gate in front of like two qubits starting with 0, you will be getting the superposition state plus plus, and in the composite system they form the four bases 0, 0, 0, 1, 1, 0 and 1, 1 with the theoretical probability 1/4 each of them. Instead of doing that, if you change the second Hadamard gate and instead you create an entanglement between the first qubit and second qubit in this configuration, like Hadamard followed by a C naught, right? So the philosophy of this kind of setting is that if the first qubit is 0, it does nothing to the second qubit. And if the first qubit is 1, it flips the second qubit. And hence, if we just simply represent like stepwise from like 0, 0, then plus and 0, then basically if you just expand the term, so if the first qubit is 0, it does nothing to the second qubit, and if the first qubit is 1, it does flip the second qubit. So 0, 0 and 1, 1. So immediately my resultant state becomes, instead of plus plus, to 0, 0 plus 1, 1. So immediately the theoretical probability of these two states vanishes like near to 0, and 0, 0 and 1, 1 has the probability of zero point 0.5 and zero point 0.5. And these states are just strongly correlated states, such that if you measure the first qubit to be 0, you are quite sure about the second qubit, and similarly for 1, 1. So this particular configuration is called the Bell state configuration, which is also called an E-bit information in quantum communication, or entangled bit of information in quantum communication. Another important phenomena is called the interference phenomena. So instead of the C0 gate, suppose you apply a control unitary operator. So of course, if you want to create the interference, you need some multiple quantum subsystems, not a single system. So what we can do, so the philosophy is similar, but instead of flipping the bit here, what we will have, we'll create an kind of interference pattern, and the intensity of the interference will vary based on the angle chosen for the unitary operator. So here our resultant state will be normalized 0 plus e to the power 2 pi I theta and 1 tensor product with some psi. So the second qubit you have taken as a psi. So instead of the plus plus state, like the 1/4 probability that we have seen, we can create an interference of the probability states using this kind of setup. And this additional Hadamard gate is shown here. This is a complete circuit, often called as a Hadamard test circuit, to compute the expectation value of some observable. Suppose this entangled operator you can create as a control unitary operator, where U is your observable. Then you can compute the expectation value as shown. The mathematical steps are shown here. So this is one of the fundamental property of quantum particles, or the quantum phenomena. And if you look at the entanglement and the interference, I often call that entanglement is a very special case of interference, where you can only create a very strong correlation in some of the computational bases and remove the other computational bases, where interference is a much general term, where you have control over all the basis states. Thank you.